Today in lesson 3.6 we'll discuss one-to-one functions and inverse functions. First of all, a one-to-one function is a special function in which for every x there is one and only one y, and for every y there is one and only one x. If a function is one-to-one, then an inverse of that function exists. We represent f inverse like this. It looks like a -1 exponent, but it is not treated or read that way. We read it as f inverse. The domain of f will be the same as the range of its inverse, and the range of f will be the same as the domain of its inverse. So in other words, to obtain the inverse function, you are switching the x and the y from the original function. You are switching the domain and the range. One of the ways we can verify that a function is one-to-one is if you compose it in either direction and you end up getting what you started with. You end up getting the input. So what inverse functions do is they cancel out what the other function did. The graph of an inverse function will be the reflection of the graph of the f function about the line y equals x, which remember we refer to as the identity function. So in other words, for every coordinate x, y, or a, b on a graph, you would switch those and that would be the coordinates on the inverse graph. So you would switch the x and y, in this case the b and the a. So when they give you the equation of a function and ask you to find the inverse, once again, you are just interchanging the variables x and y. And then you would solve that equation for y and put it in function notation. So key thing to remember here, for an inverse function, you are always switching the x and y, whether we give you the graph, the ordered pairs, the equation. Here are some examples of functions. They want us to determine whether or not they are one-to-one functions. Well, remember the way that we tested a graph to see if it was just a regular function was we used the vertical line test. We were making sure that for every x there was one and only one y. Well, all of these have already been said that they are functions. So how do we test that it's a one-to-one function? We need to also see that for every y there's one x. So remember, the horizontal line represents each and every y value. So we use the horizontal line test to see if this is a one-to-one function. So if we were to slide the horizontal line up and down this graph, anywhere we stop, does it hit the graph in more than one place? If the answer is no, it only hits the graph in one place at a time, then it qualifies as a one-to-one function. That will then mean that there is an inverse to this particular function. So notice this one passes the test. It's a one-to-one function. This does not pass the horizontal line test because for the value of y equal -2, notice there are two x values that would correspond to that. So there's more than one x corresponding to the y value of -2. And so this would not be a one-to-one function. This graph would pass the horizontal line test each and every time, and so it's a one-to-one function. For these examples, we can determine if they're one-to-one by first graphing them and then performing the horizontal line test. So notice our first graph, you recognize it, I'm sure, as a linear function. It would pass the horizontal line test, so it is one-to-one. The second graph, I'm sure you recognize as our square function, has the shape of a parabola. It does not pass the horizontal line test, so it is not a one-to-one function. Our graph number 5, you probably recognize as the reciprocal function that has been shifted down 2 units. So notice here, instead of being above the x-axis, it has been shifted down 2 units, so we drew the horizontal asymptote in here at y equal -2, and we filled in the 2 curves. This would pass the horizontal line test. And here are some other examples. The next thing that you will be asked to take a look at is the composite cancellation. This is used to verify whether two functions are inverse functions of each other. So here we want to verify that f and g are indeed inverses. The way we can do that is compose them in either direction, and if we end up getting what we inputted, which is the variable x, then we proved that it was inverse functions of each other. So notice we are placing the g function inside of the f, first of all. So we take all of this and place it right here where the x is. Then simplifying, what happens here is the 3's cancel. If you factor the numerator here, you can take out a 2 as a GCF, and then that 2 cancels with this one, leaving just x plus 4. Bring over the minus 4, and everything reduces down to just x. Here, we're plugging the f function into the g function, so we're taking all of this and putting it right here where the x is. And so we end up with 2 times the entire f function plus 8 divided by 3. When you distribute the 2's cancel here, giving you 3x. 2 times negative 4 is negative 8. Bring over your plus 8. Combine. You end up with this. The 3's cancel, and you end up with x. So we inputted x, and we output x. So these functions undid what the other function did. So they are inverse functions of each other. The next example here gives you the graph in red of the function and wants you to sketch the inverse function. Well, remember, we just switched the x and y values and realize that it'll be symmetric about this line y equals x. So notice on the red graph we have the coordinates 0, 2. So on the inverse we are going to plot the reverse of that, 2, 0. We also have the point 3, 3. Well, when you reverse them you still have 3, 3. So we plot 2, 0, we plot 3, 3, and then we fill in the curve with the idea of it being symmetrical about this line. So what you see in blue represents the inverse function. How do we identify the domain and range? Well, of the original function in red here, remember domain is x values, so we look left to right. This graph is starting at x equals 0 and ending at infinity. Range values are the y values, so we look at the bottom graph of the graph to the top. This graph is starting at a y value of 2 and continuing to positive infinity. Still looking at the red graph. So there's my domain and range. I can now answer the same question looking at the blue graph, or I can simply take these answers and switch them, because remember, the inverse function will have the opposite domain and range of the original function. So notice here we took the domain and made it the range of the inverse. We took the range and made it the domain of the inverse. In example 28, the red graph is what is given. I recognize the coordinates here on the red graph. The f function is 2, 4, 0, 3, and negative 4, negative 5. I then just switched the x's and y's in every coordinate. So this became 4, 2 on the inverse, this became 3, 0 on the inverse, and this became negative 5, negative 4 on the inverse. You then connect those points, keeping in mind that your graphs should be symmetrical about the line y equals x. Then identify the domain and the range. So looking at the red graph from left to right, it starts at an x value of negative 4 and stops at an x value of 2. The range from bottom to top begins at a y value of negative 5 and stops at a y value of 4. So this is the domain and range of the function f. To identify its inverse's domain and range, all we have to do is switch those values around. We'll make the domain of this the range of the inverse. Make the range of this the domain of the inverse. Now, in this example, we are given the function in the form of an equation, and we are asked to find the inverse of this function. Find it in the form of an equation. All you have to do is switch the x and y. So again, keep this in mind. Every time we're dealing with finding the inverse, we are switching the x and y, switching the domain and range. So in this example, you may say, well, where is the y? Remember that f of x is standing in the place of y. So rewriting that as a y and copying the problem as is, my first step is going to be simply to switch every x and every y. Make every x a y, make every y an x. So notice here, this became an x, this became a y, and this became a y. So this here represents the inverse function of this. However, they don't want us to turn it in like this. They want us to take this now and solve for the letter y. So we're going to use our algebra skills to make that happen. So first things first, because it has a fraction in it, I'm going to get rid of the fraction by multiplying both sides by the common denominator, which in this case is 7 minus 5y. So what happens here on the right side is that will cancel with the denominator. I bring down the 8y minus 1. Over here, I'm going to get rid of the parentheses by distributing, and this is what we end up with. Now I want to get my y terms on the same side. So I chose to go ahead and add 5xy to both sides. I then added 1 to the other side because I'm trying to isolate my terms that have y's in them. Once I did that, I realized I do not have like terms here that I can actually combine, but I still need to isolate that y. I can do so by factoring it out as a GCF from the right-hand side. So when I do that, I end up with 8 plus 5x, which I can now divide both sides by, and that allows me to now isolate the letter y. So y equals this, which is what I was trying to get to, solving for y, and now I can replace the letter y with the inverse notation. So f inverse of x is equivalent to 7x plus 1 divided by 5x plus 8. And that is how we find the inverse equation.